Hi everyone, welcome to lesson 6 of the Forces in Space scheme. This is about gravitational forces, or really it's about mass, weight and gravitational field strength. And the key aim of this lesson is to make sure students are clear about what those three words mean. And as all of you will know, there are a lot of kind of misconceptions and everyday language that needs to be tidied up to make sure students are ready to think about this in a physics specific way. So the first thing I would do here, and this won't be completely new to them because they've done the particles and energy unit, which is on kind of matter and stuff like that. But I just talk about mass, and in really, really simple terms, mass is just a measure of, it's kind of how many particles an object has, but also how heavy that's a bad word to use. Yeah, the amount of matter each particle is made up of, let's say. It's really hard in this lesson to avoid using some kind of sloppy language, but if we draw some nice clear diagrams, then hopefully we'll clear up some of the confusion. So what I'm going to do here to illustrate this concept of mass is draw a box. I'm going to say this box is made up of a certain number of particles, each of which have their own mass, but let's say that box has a mass of 1 kilogram. Now, if I want to increase the mass of this box, well, I just need to add more stuff to it. So let's imagine now I've got a larger box like this, made up of exactly the same stuff. So it's just exactly the same material, but now I've got twice as much of it. Well, now I would have a mass of 2 kilograms. And there's links, obviously, to density, which they learned about. They came across this concept of mass back in year 7, so you might want to revisit some of that as well. But what I really want to do now is emphasize mass is the amount of stuff or matter something is made up of, and we measure that in kilograms. We now need to compare that to a word they will use all the time, but actually means something quite specific in physics, which is weight. So I'm going to start by talking about the weight on Earth. And as we'll see, we'll look at the weight on Earth, we'll also look at the weight on Jupiter in order to introduce this idea of field strength and clear up some of these misconceptions that students might have. So I'm going to draw Earth like this. I'm going to draw my little box on top of Earth like that. You can just draw that as a square if you like. I'm going to say, here's my 1 kilogram box. Now, when I draw a force, I always start from the center of it, so I'm going to do that in pencil as well. I'm going to start from the center, I'll draw my little dot here like this. I'm going to draw my force acting downwards like this. And what I'm going to say is, if I had a 1 kilogram box that was on the surface of the Earth, as I've drawn here, obviously not to scale, if I had that 1 kilogram box, then there'd be a force of 9.81 newtons. Now, I'm going to draw the same thing again here, but I'm going to do it with my 2 kilogram box. So let's draw the 2 kilogram box here like this. Draw my force acting from the center roughly. So I've drawn my dot. I'm going to go downwards like this. Remember, I'm always modeling these ways that a physicist thinks throughout every lesson. So I'm going to say, well, this is 2 kilograms. But now the force acting here is not 9.81 anymore because I've doubled the mass. But because the Earth is the same, it's the same Earth that we're talking about. Whoops. So I've doubled the mass times 2. And the Earth is exactly the same, so the amount of gravity is exactly the same. So this means my force, in this case, is 2 times 9.81. You could put this into your calculator if you like. On this video, I'm just going to do it in my head. Here's one I prepared earlier, and it's 19.62 newtons. Now, I forgot to mention, this is the first time I've introduced newtons, so I need to make sure I explain to students that I measure forces in newtons. If you wish, you might want to do a little demo with a Newton meter, just to illustrate that. I'm not going to do that here because I don't have one at home, but illustrate the point that forces are measured in newtons. And then you could just add a label here to say, well, okay, what force is acting here? We know this is the force of gravity. Well, we call this force of gravity, we call it the weight. When we talk about the weight, actually, it's something that's measured in newtons, and it's the force of gravity acting downwards towards the centre of the Earth. And what you want to illustrate here is that if you double the mass, well, you double the weight. So far, so simple. Now, students might be going, okay, well, what are you talking about here? What is and what's this random 9.81? Where does that come from? So I think it's helpful to then draw the same diagram comparing the situation on Earth to the situation on a much larger planet, Jupiter. And they'll all be aware from Key Stage 2 that Jupiter is the biggest planet. So you can draw that nice and large here to really emphasize the point. And then I'm going to draw my little 1 kilogram box on the surface of Jupiter now. And I'm going to draw my dot in the middle. I'm going to take my ruler. I'm going to draw my force acting downwards. And I might draw the arrow a bit longer. And I'll do that deliberately. In fact, although I've realised I didn't do my arrows here to scale. So for the time being, we'll wait till we get to balance and unbalanced forces before we worry about that. But what I'm going to do here is illustrate this and say, well, if I was on the surface of Jupiter and I had a 1 kilogram box, it turns out if you were to make a measurement, and again, right now we're illustrating mass versus weight. We don't need to go into how we come across some of these things. I mean, it would be nice to do that, but yeah, we have to be realistic about time. The main point you want to get across to them is that the force here, also called the weight, the force of gravity, would not be 9.81 newtons on Jupiter. You might want to ask them, do you think there's going to be a bigger force or a smaller force? Well, hopefully you can elicit the idea there's going to be a bigger force because Jupiter is a much bigger planet and therefore it's got a much stronger force of gravity. I don't want to use the word gravitational field yet, but yeah, effectively it's because it's got a stronger gravitational field. And actually the force here would be 25 newtons. So now let's draw the same picture again, but with our 2 kilogram box. So I'm going to draw my 2 kilogram box this time. Draw my dot in the middle of the box. I'm going to draw my arrow coming down like this. And I forgot to put times 2 here. But I'm going to do the same process again. So this is 2 kilograms, this box. 2 kilograms. So I'm going to draw my times 2 here. Show, well look, I've doubled the mass again. So what am I going to have to do to the force? Well, the force must double as well. So that means my gravitational force here, or my weight, is going to be 50 newtons. Okay. And again, if you want, you could add another arrow here. This is the weight. You could add it here as well. This force, the gravitational force, is called the weight. Keep re-emphasizing that. Just to make sure students are really clear that weight is a force. We don't measure it in kilograms, we measure it in newtons. And as you will all know, that's something that you're going to have to keep repeating again and again and again, because the whole of society measures weight in kilograms or stone or whatever. Now the last thing you want to do here, so far, you've illustrated the difference between mass and weight by saying, well, okay, mass is measured in kilograms, weight is measured in newtons, but students might be like, well, okay, you've introduced this kind of arbitrary number, but I still don't really know what the difference is. So it's worth emphasizing the fact that here you've got a constant ratio, and this again, you don't want to go too far necessarily into the maths here, because you're kind of presenting it visually. You don't want to get too much into the algebra yet, I would say. But what hopefully they will notice is that you've always got this ratio of 9.81 divided by 1 is the same as 19.62 divided by 2. The point is, this is giving you a really clear definition of gravitational field strength. So what you can say is that the gravitational field strength diagram really helps illustrate this point. You may come up with even better diagrams. If you do, please send them my way. Gravitational field strength on Earth, what that's telling you is for every 1 kilogram of matter you have 9.81 newtons of gravitational force. So in this case, the gravitational field strength is equal to 9.81, and you can emphasize the units here. It's just how many newtons for each kilogram. So here we've got 19.62 newtons because we've got 2 kilograms. The point is that this constant ratio, which we can see here, and it's this number here. And then you might want to, by the way, you can just shorten it to a lowercase g with an e for Earth. So this is the g, the gravitational field strength on Earth is 9.81 newtons per kilogram, because this is going to save you time here. So then you could ask students to tell you on whiteboards, for example, okay, what do you think the gravitational field strength on Jupiter is going to be? For each kilogram of mass, how many newtons of force am I going to have? Well, hopefully they'll spot that you've got 1 kilogram here and you've got 25 newtons, so it's just going to be 25, but be really particular about the units, newtons per kilogram. For every kilogram of matter, you get 25 newtons of force, and that's because Jupiter is a bigger planet than Earth, so you get more force for every kilogram because it's that bigger, more massive planet. And again, the last thing to talk about is that classic, the kind of misconception that's always comes up, and I'm sure you've all taught before. Why does mass stay the same wherever you are in the universe, but weight changes? The point you want to illustrate is that in this case, whether you were on Earth or Jupiter, the mass of the object was exactly the same. It was 1 kilogram here, it was this one was 2 kilograms. What's different about the different places in space is the gravitational field strength, and hopefully this diagram illustrates that quite clearly. Here you had a lower field strength, here you had a higher field strength. And that's why the weight of the 1 kilogram object, which would be 9.81 on Earth, is going to be bigger on Jupiter because it's 25. If you're out in the middle of space where you have a very low gravitational field strength, well, actually the weight would be quite low, even though the mass is the same. And hopefully laying out the diagram in this way gives students that clear picture that will allow them to put that into words. But they're probably going to need quite a lot of your support, and hopefully there's lots of nice hinge questions that can check for understanding and tease out any remaining misconceptions. Okay, in the next lesson we're going to look at the idea of inertia and Galileo's experiment.